Okay, in this video, we're going to use the t-test, actually. We're going to use the t-distribution to calculate a confidence interval. So this is a little bit different goal for our inferential statistics. What we're doing here, I have this graphic over here to sort of illustrate this, is let's suppose we have a population and we take a sample from that population. What we can do is, based on the sample characteristics, we can estimate the population mean, we can estimate the population mean mu, right, given what we learn in our sample. So the direction that we're going is we're going this direction. We're using the sample to infer some characteristics about the population. And you know, typically we do use the sample mean to do that. But the problem with the sample mean is you don't know how accurate or inaccurate it will be as an estimator of mu, right? We know that it'll be off a little bit, but we don't know by how much. With confidence intervals, we can get a probability, a level of confidence. Say like we're going to construct, often you construct a 95% confidence interval. So we'll get, it's a little bit more precise in that regard. So let's consider this example. Let's suppose the university administrator wants to know the average IQ of the professors at our institution. Okay, so you could sample every, you could have every faculty member come in and take an IQ test, but the IQ tests take a long time, right? It takes several hours to assess an individual, and if you have even a small institution like TC&J, we have like 330 some odd professors, so that would take an enormous amount of time. Instead, she randomly samples 20 professors, or let's suppose that everybody that's asked does and completes the full battery of IQ tests. So she has a sample, random sample. She has an N of 20, and let's say that the mean is 135, so this is the mean IQ score for those taking the test, standard deviation of 8. So one thing we're going to need, and we can quickly calculate standard error of the mean. So standard deviation is 8, we divide by the square root of N, or 20, and this is our standard error mean, and standard error of the mean. We can also quickly calculate our degrees of freedom because we're also going to need that. So we take our N, 20, minus 1, and we're going to have 19 degrees of freedom here. So those are the constituent parts that we need. Now we need the formula for the confidence interval, and here it is, and it looks a little weird, but what it is you have your X bar here, which represents the sample mean, and you're going to add to the sample mean, and you're in one step, and then in another step you're going to subtract this value, everything that's to the right of that calculation. And what it is it's really two components. It's your critical T at an alpha level, and this alpha level is going to depend on your confidence interval. So if we want a 95% confidence interval, we're going to use an alpha level of 0.05. If you wanted a 95% confidence interval, we're going to use an alpha level of 0.01. And then you have your N minus 1 degrees of freedom. So this is really the critical T. We're going to use the table to look it up. It's the critical T at the alpha level with your degrees of freedom to match that particular sample characteristics. And then you multiply that by the standard error of the mean for the sample, right? We just calculated that. This is S, which would normally represent standard deviation, but with a subscript X bar, that's standard error of the mean of the sample, okay? So, what we're going to do is we're going to look up, you can go to the table and you can look up, and what I've written out here is you're going to have 135 is your mean, and we're going to add to that and subtract to that T, whatever the critical T value is, with an alpha of 0.05 and 19 degrees of freedom. And of course, our 1.79 is the standard error of the mean, right? 1.789 is the standard error of the mean there. So if we go to the table and look up our T with an alpha level of 0.05 and 19 degrees of freedom, you will find a value of the critical T will be 2.093. That goes into that value there. That's it. That's the trick. It's not very hard, not very complex. Now all we got to do, the math is pretty easy. We multiply these two numbers, right? 2.093, 1.789, and we get this 3.744377. So now to get the lower limit, we take 135 and we subtract that value, right? There's your lower limit. And we take, to get the upper limit, you add. So 135 plus this 3.744. That's your upper limit. So what that means is we're 95% certain that the population mean is somewhere between 131.256, that's the lower limit, and 138.744, that's the upper limit. So now we know roughly where the population mean is, and we also have a probability. So not only do we have a range of scores here, but we have a probability associated with that. So more than just the sample mean, we have some confidence in how accurate our statistics are. So you can use these to make some inferences when you only have a sample. You can make some inferences about a population, and that's obviously very useful in a lot of contexts. We don't use it a lot in psychology because most of the time we're focused on experiments and differences between our groups. But sometimes you'll want to have a sample and make some inferences about the population at large, and it can be particularly useful to calculate confidence.